To really understand the mechanics of Earth's climate, we have to look up, all the way up to the roof of the world. Welcome to this explainer. We often think of the Himalayas as just this static, immovable geological boundary, but they're absolutely not. They are a dynamic, living machine. By directly interacting with our atmosphere, this massive elevated surface actually functions as a primary driver of the entire global climate system. It's like a giant gear turning within a larger planetary clockwork.
So, to really ground the atmospheric physics we're going to cover today, it helps to use a tangible mechanical metaphor. Let's call it a planetary engine. This framework describes the Himalayas and the Tibetan Plateau as a massively complex, interconnected machine. It's got tectonic foundations acting as the chassis, huge thermodynamic furnaces serving as the engine itself, and global transmission systems that dictate weather patterns literally thousands of miles away. Okay, let's dive into this. Here is the blueprint for the machine we're about to dismantle. We'll look at 1, the planetary switch, 2, the tectonic foundation, 3, the thermodynamic engine, 4, orographic insulation, 5, the architects of rain, and 6, global teleconnections. Section 1, the planetary switch, a living machine. Just look at this metric for a second. 3 million square kilometers of elevated terrain. That is a mind-boggling amount of land. Averaging 4,500 meters in altitude, the Tibetan Plateau interacts directly with the mid-troposphere. It is so vast and positioned so high up that it basically functions as a master switch for the Asian monsoon. It completely rewrites the atmospheric rules for the entire hemisphere. Section 2, the tectonic foundation, building the chassis. So how did this chassis get built? Well, the genesis of this entire meteorological system is rooted in deep geological time, tracing all the way back to the fragmentation of the Gondwana supercontinent. Around 55 million years ago, we see an initial intra-oceanic arc collision. Then, by 50 million years ago, during the Eocene, Greater India collides directly with the Eurasian plate. Fast forward to 8 million years ago, and this massive tectonic uplift triggers the onset of the Asia monsoons, which, believe it or not, eventually sets the stage for the ice ages around 2.5 million years ago. And this brilliantly illustrates the sheer speed and intensity of that crash. Greater India drifted rapidly northward over the course of 70 million years, with convergence rates hitting up to 54 millimeters a year. It was basically an unstoppable force, sliding through the ocean, violently pushing the Earth's crust skyward right at the point of impact. That monumental collision resulted in an incredible 3,600 kilometers of crustal shortening. Essentially, massive layers of continental crust folded and stacked on top of each other through deep subduction. This process forged the impenetrable, towering chassis of our planetary engine, giving us the highest elevated surface on Earth today. Section 3, the thermodynamic engine, the furnace. 9 kilometers. That is a truly staggering number to wrap your head around. Because of its immense altitude, intense solar radiation directly strikes the Tibetan Plateau high up in the mid-troposphere. This creates a massive low-pressure void exactly 9 kilometers above sea level. Here's how that works. This barren, high-altitude soil aggressively absorbs heat, and then it warms the overlying air column through something called sensible heating, basically bypassing the lower atmosphere entirely. This creates a deep, warm-core anticyclone known as the South Asian High. Think of this high-altitude void as a vast, powerful chimney, aggressively pulling moist, energy-rich air northward all the way from the Indian Ocean. Section 4, orographic insulation, the mechanical shield. Now, what's really interesting about this is the intellectual tension between two competing atmospheric models. For decades, scientists relied heavily on the classic Tibetan Plateau heat engine theory, where, as we just discussed, sensible heating draws in moist air. But recently, high-resolution modeling has introduced a competing idea, the orographic insulation paradigm. This theory suggests that the primary role of these mountains isn't just to be a heat pump, but rather to function as a giant physical mechanical barrier. Under this insulation model, the mechanical blocking effect of the mountains literally deflects the cold, dry air masses sweeping down from Siberia and Central Asia. By aggressively keeping that dry extratropical air out, the mountains trap highly concentrated, moist static energy over continental India. This perfectly positions the monsoon's thermal maximum directly over the northern subcontinent, which drives incredibly deep, systemic tropical convection. It acts just like a massive shield. Section 5. The architects of rain, the output. 11,872 millimeters. Take a second to process that. That is the raw, mind-blowing average annual rainfall of Mawsynram in northeastern India, which is widely considered the wettest place on Earth. To put the sheer volume of that water into perspective, on a single day in June 2022, they received over 1,000 millimeters of rain in just 24 hours. There's literally nothing else like it.
Let's move in and see how this actually builds by breaking down the physics of orographic lift. Step 1, a completely saturated low-level jet from the Bay of Bengal sweeps north and violently hits the steep 1,400-meter limestone escarpment of the Khasi Hills. Step 2, the air is forced into rapid vertical displacement, causing severe adiabatic cooling. And because cool air holds exponentially less water vapor, we hit Step 3, immediate, continuous condensation and a relentless torrential downpour.
This incredible atmospheric exhaust directly shapes human survival on the ground. Local residents actually weave these body-length shields called noops out of bamboo and banana leaves. This lightweight but super rigid armor lets them walk completely hands-free through downpours that can last for weeks without a single pause. It's a truly perfect example of human ingenuity adapting to one of the most extreme microclimates on the planet. Section 6. Global Teleconnections, the Transmission.
The impact of this massive system definitely doesn't stop in Asia. The high, cold topography of the plateau actually acts as a massive mechanical block that splits the winter westerly jet stream right in two. And by splitting the jet stream, the Tibetan Plateau becomes a major planetary waveguide, literally accelerating storm tracks thousands of miles away across the North Pacific.
So the crucial point here is how thermal anomalies in Tibet directly dictate extreme weather in North America through something called the TRC wave train. Let's look at the data. If the Tibetan soil has a warm spring anomaly, the Rocky Mountains will be cold, which actually predisposes the U.S. southern plains to severe summer droughts. Conversely, a cold spring in Tibet triggers a warm spring in the Rockies, dramatically increasing the likelihood of extreme moisture convergence and catastrophic flooding, like the massive Memorial Day flood in Houston. The climates of Asia and North America are fundamentally locked together.
But we have to talk about how this delicate equilibrium is under urgent threat. As global temperatures rise due to anthropogenic warming, the cryosphere, the snow and ice acting as Asia's water tower, is rapidly thawing. Glacial retreat is destabilizing the entire region, creating a drastically changed hazard landscape with increased risks of catastrophic flooding, landslides, and massive debris flows. This directly threatens the water security for nearly 2 billion people living downstream. The data clearly indicates this massive system is undergoing rapid, systemic shifts. Which leaves us with this final, incredibly provocative thought. What happens to the billions of lives downstream and to our entirely interconnected global climate when this planetary engine breaks down? This immense geological clockwork is fragile, and understanding its mechanics is the very first step in preparing for a changing world. Keep learning, keep questioning, and thank you for joining me on this explainer.